So Jon Zeolla is CTO for CISO, and he also helps out with Steel City InfoSec and B-Sides Pittsburgh. We or help organize that. I'll turn it now over to Jon.
Can you hear me at all? There we go. All right, great. Thank you. Thanks, John. Is this off?
I'm going to turn that down.
Okay, thank you. I don't want to. All right, cool. Thank you. All right, everybody. Thanks for coming and sticking around for after lunch. I know this is a bit of a tough spot to try and pay attention and learn about a complicated topic after you've just digested some delicious turkey, I hope. My name is Jon Zeolla, which is funny because I don't really have it on that slide, but these are some other things about me. So I'm an InfoSec professional. Like John said, I'm the CTO and co-founder of CISO, which is a consulting company. Founder of Steel City InfoSec, organizer of B-Sides Pittsburgh, and I do various projects. So that's who I am, and so I wanted to start this off and kind of frame a little bit of why we're talking about this. And actually, we're lucky enough to have one of the members, one of the authors of this report in the room. Kyle, raise your hand. There we go, that guy right there. He's one of the three people that authored this risk survey for emerging technology domains. That they, CertCC works with US Cert to kind of provide this on a yearly basis. And I saw this the other day, and I thought it was really relevant to this talk because as I skimmed through it, I found that the number 2 domain that was prioritized for further study, based on a number of factors, was machine learning. And so that's essentially what we're going to talk about today. I've been to a lot of machine learning and AI talks, and I've been to a lot of vendor pitches, and I get aggravated a lot because we never actually get to the meat of like, how does this stuff actually work? It pretty much is just spoken like it's magic, right? It's just going to magically fix all of your problems. It's always the best solution. And so I've been working over the last maybe 3-4 years to better understand exactly, technically how does this stuff work. And so this presentation is going to be my attempt at explaining with lots of pictures, because pictures help me at least, with lots of pictures what exactly that means. Another brief note about this report, the reason why it was kind of prioritized as number 2 was based off of this matrix, which says essentially, how could this technology impact people? Is it safety, privacy, financial, and operational related severity? So this got a 3, a 3, a 4, then a 2, which kind of ranked it pretty high. Am I getting things right so far, Kyle? All right, there we go. And then just a little bit more of setting the stage before we start digging into some of the details. I'm going to do some definitions. We hear AI and we hear machine learning, and there's some confusion. Are they the same thing? Are they different? How are they different? What's AGI? What's data science? All these things. So I just have 5 quick definitions, and then we're going to start digging in. The first definition that I wanted to give is AGI. Has anyone in the room actually heard of AGI before? So a very small number, maybe 2 or 3% of hands went up. It's not a very widely used term. At this point, people in the community, in the math, stats, machine learning communities aren't even 100% sure that this is attainable. But what it means is what most people will call this AI, but they actually kind of mean AGI, which is a fully autonomous kind of system. It says in the definition, a machine that can perform any intellectual task that a human being can. So this is artificially, generally intelligent. It can do any sort of task that a human could. Then you have AI, which is kind of like the next step down. Consider this like a subset of AGI, which is a device that can perceive its environment and then take actions to maximize the chance of success at a single goal. So you kind of have to establish what this goal is, where you are going, and then put it in an environment, and then it kind of attempts to get to that goal in a maximally successful way, which is slightly different than AGI, right? And then machine learning is a further subset. So machine learning, we're just saying it can learn without me giving it a set of roles on what exactly to do. So like historically, we've had like expert systems and things like that where you have a knowledge base and then you have a bunch of roles that are set by an expert, and that's kind of like the predecessor you can consider to machine learning, where we'll talk about specifically what this means, but you have an algorithm that learns without being told exactly what to do. And then two more definitions I kind of just threw in here at the last minute because I get these sorts of questions a lot. What is deep learning or data science? So deep learning is, again, a subset of machine learning. So we've got AGI, under that AI, then machine learning, and then finally deep learning, which is it's a family of machine learning algorithms based on learning data representations, and they often mirror neurons in the brain. So if you've seen, another term would be like artificial neural networks, right? Deep learning is a little bit broader than that term, but I have a picture later on that shows exactly what that is, but it's a bunch of algorithms tightly connected together that then give you a result at the end. That's essentially what deep learning refers to, the deepness of and the width of the number of those algorithms, you might have heard the term perceptrons, that are in this neural net. That's why it's deep, because there's many layers, and you'll see that later. And then finally, data science, which is just a field about extracting data extracting knowledge or insights from data. So this is just kind of a scientific method that you can use to apply to data to understand what is in there, to extract patterns or any sort of information from this set of data. So let's talk briefly about where we are now, because it's interesting to look at kind of the basic hype cycle. So with any new emerging technology, there's this basic hype cycle, and I have so this slide it comes from Gartner. Is that easy to see? Probably not so great. But it has kind of 5 basic stages, and it starts out with an innovation trigger. So like, this can actually work. We know that this can actually work, and so that's your innovation trigger, so it'll start. Your expectations for that technology will rise and continue to rise. And when they get to the top, kind of where deep learning and machine learning is right now, you're kind of considered at the peak of your inflated expectations. So the way people perceive how this can be used is higher than how it will actually ultimately be able to be used at the end in the plateau of productivity, right? There's also kind of deep reinforcement learning on here as well, which is earlier stage, and in the kind of those three technologies are relevant to this presentation, talking about AI and machine learning. But to be honest, machine learning hasn't necessarily followed the normal hype cycle. Its hype cycle looked a little bit more like this. So way back in the 1950s was kind of the real innovation trigger, and it's went up and it's went down and up and down and up and down ever since. And the downsides for these are typically considered AI winters or AI downturns. Usually AI winters is the term you'll hear, and there's 3 predominant ones. And there's a whole interesting history as to why those happened and why we were able to get out of them again, just to re-enter another winter. But kind of at the point where right now it is a little bit better of an inflection point where it seems to be solidifying a little bit more, and an AI winter isn't really expected. And the main difference, in my opinion, for this is kind of the confluence of a lot of data that is available to the people doing machine learning, because a lot of data is required to do machine learning. And the ability, kind of like over time, Moore's law has kind of graced us with much more compute power and the ability to actually work on that large amount of data. So we simply couldn't scale up before like we can now. And in my mind, that's kind of the biggest reason why I believe that this is going to be a little bit more sustainable. And also, in the past, for the prior winters, there has been high expectations, but they haven't lived up to them. And now we're actually seeing things happen. Happening using machine learning that are tangibly good, right? I don't know, just anecdotally, I recently was looking at the Pixel 2 from Google, and around the same time they came out with the Google Pixel Buds. Did anyone hear about these Google Pixel Buds? They're like completely blowing my mind. So these are headphones that are Bluetooth, you listen to music on them, whatever, but they can, in real time, translate languages from other people. So you could go to another country, put these earbuds on, and literally get real-time translations of what people are saying to you and understand them. Like, that is completely driven by Google Translate, which is completely driven by machine learning underneath. And the fact that could work completely blows my mind, but it also validates that this is probably going to stick around for a little bit, because we're actually seeing tangible benefits from it. And so, this has been around for a while, like I said, the 1950s. So there's been a lot of technologies The point of this slide is just to show that there's a lot, not to look at any specific one. And this is relevant to kind of the big data landscape. So these are the technologies that hold and can manipulate and look at the data that you might be storing. But even specific to AI and machine learning, here's another beautiful infographic, I guess, that shows all of the machine learning technologies that have been coming out. And there's a lot of them, right? So it has been growing and growing and becoming more popular. There's a lot of different vendors claiming that they do this. And I can guarantee that all the vendors claiming that they do machine learning are not in this slide, because it would be way more. No way I could fit it on this slide. But so another question that I get from a lot of people is that, isn't machine learning really just like advanced statistics? And I'm going to attempt to dissuade you from that idea using the next couple of slides, because although it kind of leverages statistics, it leverages a lot of math, statistics, probability, and comp sci fundamentals, it is not just statistics. So if you were to look at something statistically, a lot of times, so I guess this picture was an illustration of if you asked a computer to randomly generate what a network would look like, what network traffic would look like. A lot of us, I'm sure, do network security monitoring or some level of network-based IDS, things like that, and can derive a general idea of what network traffic looks like. And this computer simulation is what's called like a normal distribution or a Gaussian model. And you can see, there's a lot in the middle with this mediocre level of linkages between other systems. And then to the left, you have lowly linked systems, so things that only talk to a sparse number of other distinct systems. And then a little bit to the right, which is highly linked. So that'd be like your Active Directory domain controller, your web server that's constantly getting hit by like everybody. But in reality, we don't, networks do not look like this. They're not distributed normally. They're distributed a little bit differently. They're distributed using what you'd consider like a power law distribution. So where you have a large amount of lowly linked systems, a mediocre amount of mediocre linked systems, and then a long tail of highly linked systems. And if any of us, all of us that have done information security operations before, you know that a lot of the strange things or the bad things that happen are kind of considered anomalies or on the edges. So you're not typically going to be looking at that far left as much as on the far right, and the far right's a little bit more difficult to pull out sometimes. But if you don't, you're going to miss the pile of bodies, right? So the pile of bodies is in that long tail, and the interesting things are in that long tail. Not to say that they aren't in the short tail, but if you completely ignore them, then you're going to be missing important information. And then I love this GIF. This next one is one of my favorites because it shows exactly how you can lie with statistics. So I'm sure a lot of people have heard of like p-hacking and things like that, but this shows like exactly what I try to explain to people when I say that statistics sometimes aren't enough. So before I show, well, actually, I'll just go to it right now because it should just run. Is that working? Yeah, great. So all of these dots are, so for each kind of iteration of this display, it's recalculating the summary statistics for these dots. We can obviously, as humans, see patterns in these. That is an X, right? And these are horizontal lines, and there's 2 of them, and vertical lines, and there's 2 of them. But if you look at the X mean, Y mean, standard deviations, correlations, things like that, they are, to a reasonable degree, exactly the same. So if you were to take these different data sets and run summary statistics against them, that circle would look the same as the dinosaur would, as the same as the star and the same as the horizontal lines, right? So summary statistics are simply inadequate at a very high level. And this would be a kind of a rudimentary way of using statistics, but it is simply inadequate for looking at the data we have right now. That's a dinosaur. Like, come on. So what I'm trying to say is that the techniques that we use matter. And so what we have here are these red dots that were generated, and the dashed green line you can see is kind of the ground truth. So that's the actual line, and these dots were generated with that line in mind and some associated jitter. Or some randomness added. And the other 2 lines, the black line and the blue line, are 2 different ways of doing a linear regression against the red dots. So they're both the same type of algorithm with differences in how that they're executed, and you can see that they're drastically different, right? The blue one is essentially garbage. That is nowhere near correct and not useful. But if you But if you wanted to naively use a linear regression technique against these red dots, it is possible that you would get that blue line, and that's what you could base future, ideas about, and that would be a bad thing, right? So the techniques here are really important. And so next we're going to start getting into the meat of, so what are the core characteristics of machine learning? I don't remember how many I broke these into, but there's about like 5 or 6 core characteristics of machine learning. And the first one is the one that anytime you read an article about machine learning, you're pretty much going to hit. And it's the difference between unsupervised and supervised algorithms. So how many people in this room have heard these terms before, supervised, unsupervised machine learning? All right, so significantly more than before, but still not up to half. So there's 2 kind of distinct differences, although there's many more than that. There's 2 key differences that I use to differentiate unsupervised from supervised algorithms. The first one is that with unsupervised machine learning algorithms, what you're attempting to do is you're trying to cluster. So you can see the circles, the kind of outline circles. There's 2 groups here, right? There are 2 clusters. The algorithm is saying absolutely nothing about what those clusters are. They're saying that these things are similar and these things are similar. But it's not saying that these things are good or bad and these things are good or bad. It's saying nothing about that. It's just, these are similar. I think these are similar. And then it would take kind of a human to take the next steps and say, are these similar things bad, right? The difference on the supervised side would be you are actually going to try to say this is something. You're going to classify these points of information that you have, the data that you've collected. You're going to say, these blue things are bad and the orange things are good. And then the other things are unknown, right? But you're actually going to put them into a classification. And it doesn't have to be good or bad. It could be good 80% positive, good 90% positive, good 50% positive, bad 90% positive. You could have a ton of different groups, depending, you can kind of specify how many groups you have. You could say, one of the things that you might classify is, what is this? So if you have a picture, we'll talk about pictures a little bit later, but if you have a picture of an animal, the classification might be, what type of animal is it, right? It doesn't have to be, good. We're not necessarily talking about good or bad. We're just talking about putting things into, applying classifications to things. That's generally what these do. And then the core of them, because of this classification and clustering difference, is that for unsupervised, you need, it typically would use unlabeled data. And unlabeled data just means a blob of things that is not typically or not purposefully structured. And with supervised algorithms, you would need labeled data, which means it is structured. So if you guys are familiar with, like JSON or CSV files or anything like that, a supervised algorithm would require, the CSV format, right, or like the JSON format, specifically saying that this, tying attributes, they're kind of considered in machine learning like features, right? Like extracting features or identifying features of the data that you have. This is the height of the animal, and this is the length, and this is the weight. Whereas with unsupervised, you're just saying, here is a bunch of numbers. Here's letters. Here's binary information. It is, here you go, right? And then you give it a couple examples of this, and you say, kind of compare them and say, are they similar or not? But you can't classify them, you just cluster them. Another thing that's interesting about machine learning is that data is necessary to create the program itself. So there's kind of traditional programming and machine learning here. Just trying to illustrate, with traditional programming, you have data and you have a program, and then what you get from it is the output. That is not how machine learning works. With machine learning, you have data. Hopefully, piles and piles of labeled data would be preferred. And you give it, kind of what the output should be. And then it's going to give you a program. And that program isn't necessarily the answer on its own. That program that was output by machine learning then needs to be applied to your data again, right? So, some of the mechanisms that you might use for this is essentially called training, right? You're training the model, you're training the program to get the output that you need, and then you can apply that model or you can apply that program to data as it comes in. There's a lot of different ways to do that, which I'd be happy to talk about, but I'm going to leave out for now. The other thing is that there's a lot of different choices. Machine learning is this giant term, and there's lots of different choices of algorithms to use within machine learning, and some of those algorithms have assumptions in them. So this data is pretty easy to understand. You look at it, you say, okay, it's kind of like a bullseye, right? There's a circle in the middle, and there's a ring around it. That's easy for us to understand, but that's not necessarily easy for machine learning always to understand, depending on what algorithm you're using. So there's a concept of kind of a big word. It's parametric or non-parametric algorithms. But what that means is that a parametric algorithm assumes a shape, and a non-parametric algorithm does not assume a shape. I feel like I'm going to fall off this. This is bad. I'm not used to being elevated like this. So this is how that would look like. So this is me. This is trying to apply a parametric linear algorithm against these this bullseye. That is not a very good. That is not a very good classification to me, right? The things on the left are definitely not blue, and the things on the right are definitely not red. Right? The background is showing how it would classify these things if it had been given the choice, and it would be extremely wrong. It chose a line because it assumed that it was a line, right? It is assuming a shape that is linear. So a non-parametric algorithm would look at the exact same data, but it's not going to assume any sort of shape, and it's going to do a much better job. It's going to say, well, there's a cluster of things in the middle, and there's a ring of things around the outside, so this is the boundary that I'm going to establish for the differences between the two. So the point here is that you could say that you're doing machine learning on data, but if it looks like the thing on the left, then you're doing it wrong. But you can still say that you're doing machine learning on data because that's true. And so I feel like this is kind of a great way to illustrate, what some of the core assumptions are with different machine learning algorithms. So it's not just something you can't just like throw machine learning at it and it's going to work great, right? You could end up with what's on the left. Another kind of core component of machine learning is how can you interpret the results of your machine learning? So this is called explainability or interpretability, essentially. And this is a great quote that I found from the Google Brain, one of their blogs. It said, "We want our machine learning systems to be explainable, and frankly, many of them are already more explainable than humans are." So I don't know how many of you guys are into behavioral economics, but there's a great book called Thinking Fast and Slow from Daniel Kahneman. If you're interested in how humans make decisions, I would suggest reading that book. It is rather thick. I did not read it, but I did audiobook it twice because it was so good I did it back to back. It's a really great book, and it explains, how to understand how people make decisions and how flawed that decision-making process is. Because if you're talking about implementing machine learning at your company, if you want machine learning to be perfect, then you're expecting more of it than you are of people. There are definitely some ways, some algorithms that you can choose. I'm going to show 3 examples in a second. Some options that you can choose which are explainable. That's very easy to say, when I put this in, this comes out. And then there are other ones that say that you put something in and then magic happens. It is not explainable. You cannot say why it made this decision, especially at this point in time, but this is the result that it gave me. And especially with certain types of algorithms like neural nets that are considered online, which means they're constantly evolving. If you ask it the question now and you ask it the same question 10 minutes from now, you may get different answers. And that's because the algorithm itself is changing and evolving over time. So let's kind of maybe make it a little more concrete. What does explainability or interpretability mean if you were to visualize it? So this first one is a simple logistic regression. So this is, just like we said before, there you have a line, and that line delineates the difference between one thing or the other. The red dots on the top are considered one thing, and the blue dots on the bottom are considered a different thing. And that blue line that goes through them is the difference. So if I took this and I wanted to know why it said a dot was blue, I could just plot it and say, well, it's below the line. So it's blue. That's why this is making that decision. I can explain why. Now, it might be that the line is incorrect, and that's very reasonable and probably going to happen from time to time. But you know why. You can explain it. You can understand it. And this is a great one. This is probably my favorite when it comes to explainability, is a decision tree. So this is another machine learning algorithm. And this is kind of a human example of how you would understand using it. Decision trees will kind of identify where these splits should happen on their own, what this arbitrary number is to split data up into sections to then make this tree. But once it's established, you know exactly what the rules are. So I don't even know if I can read this. So it says, the score of a customer's interest in watches. If the score is between 1 and 4, the decision's no. Between 4 and 7, then you have to do something else. You have to look at their salary. Is their salary low, average, or high? And if it's average, you then need to look at their age. Is their age greater or less than some number? And that decision tree will get you to the end, which is a decision yes or no. This is applying machine learning. You would apply machine learning to create this decision chart. And then you could automatically apply this to your data. And if something were to be given a decision yes or no, it's very easy to identify why. Oh, well, your score was a 6 and your salary was high, so the decision was yes. That's why we did this. So that might be intuitive, and if that's all you had seen about machine learning, you'd say, well, you can explain all machine learning until you get something that looks like this, where this is kind of deep learning or a neural network, right? And so what you have on the left is kind of your features, your inputs, right? And what you have on your right, the far right, there's four little buttons. Those are called perceptrons, but that is kind of your output. So in this example, you have some level of inputs, and it's going to give you one of 4 outputs, right? One of those 4 is going to be essentially the ultimate decision for this neural net. And you're going to take your data, you're going to map it to all of those points at the beginning, and it's going to flow through. And there are different mechanisms to do this. You have, you can just have like a feed-forward neural network where it's only going to go in one direction. You can have back propagation where things are going to kind of loop back around. There's a lot of ways to implement this. This is kind of one of the simplest. But not only does that happen, and not only there are a lot of choices, but essentially each one of those little dots is its own machine learning algorithm. That could be, each one of those could be a logistic regression. And that's a lot of logistic regressions. So that makes it complicated, but not impossible, right? But there are some mechanisms that are used in training and using models that get very complicated. So there's a concept, there's a well understood and accepted concept of just randomly removing perceptrons. Randomly, literally randomly. Like, I'm just going to get rid of these ones because I feel like it will help the output generalize better to other use cases. I am going to remove connections. I am going to have dropout. So these ones, as they come through, will be randomly picked and just thrown away. Just not going to be factored, right? So how can you explain something that is randomly messing with you effectively, right? Randomly removing components and changing components and not accounting for them. And then in addition to that, these are evolving, so they're changing over time. So like I said before, just because you did it now and you got answer A doesn't mean if I did it in 2 hours that I'm also going to get answer A. I could get something different. And then I think this is the final one. Yeah, this is the final kind of characteristic of machine learning is understanding that everything has trade-offs. So whenever you're training a model, you kind of establish a lot of different parameters to that training method. And you may underfit, you may overfit, or you might have kind of a balanced approach. And this is a great picture. I think it's from AWS, Amazon guys, that illustrates this really, really well. And so on the left, you've got underfitting, which is like, okay, I've got these points. I'm just going to fit a line to it. And there you go. And on the far right, you say, well, I want this thing to be perfect. I want it to be absolutely perfect. So you might overfit to it. And the problem with overfitting is that it might work well for the data that you're currently training it on, but you're not going to be able to use it for data in the future because it's going to be inaccurate. It's only working, you made it work really, really well on the data you gave it, but now you can't reuse it for other things, so it's not useful. But on the left, if you make it generalize super well, then it's going to be really inaccurate. So in most cases, you're going to have to do this, what they call the bias-variance tradeoff, and have kind of a balanced approach. But even with the balanced approach, you're still going to have some level of false positives. So understanding that pretty much all machine learning is going to have some level of false positives. So I'm a little bit low on time, so I'm going to burn through some of these really quick. The potential benefits of this are enormous. I'm not going to show that, but I'd love to give it out to people. It's a video of how machine learning helps improve traffic in self-driving cars, and it's really amazing. And here's another example. This is kind of a gadget that's used on a bridge to connect cables together and different sort of things. That is one that was engineered by a person, by someone who's probably very good at their job, right? That is the optimal solution they were able to come up with. But as you kind of edge towards using machine learning to do the same solution, you get something that looks like on the right, and that's kind of alien to me. I don't know about you guys, but I don't think I would ever design something that looked like the thing on the right. And at the same time, you might say, like, well, does that even accomplish the goals that you had? And actually, it did. So it provided a 50% reduction in height, 75% reduction in weight, and exactly the same structural ability. So I know that's not super pertinent to InfoSec, but it kind of illustrates what these solutions might look like. You might create a solution that looks like the thing on the left that's highly structured and rigid and does exactly fixes the problem you're trying to solve. But on the right is a much better way to do it. But it's so abstract that it would be near impossible or impossible for a human to do on their own. And so, given all these enormous benefits and kind of how machine learning works, let's talk about why it's such a mess. So this is a computer vision machine learning algorithm, a convolutional neural network, that classified this thing as a wolf. Now, can anyone guess why this would be classified as a wolf? It looks like a wolf. Sure, that makes a ton of sense. Any other reason, maybe, why this would be a wolf? So I would think the same thing. I'd say, well, it looks like a wolf, so it's a wolf, right? Well, that's not exactly how these machine learning algorithms work. The reason why it said that this was a wolf is because there was snow in the picture. So, explainability and interpretability and understanding why it's making these decisions is a really interesting thing, right? If I put a dog in the that might have looked like a wolf, like maybe a husky or whatever, and the snow, that might even be what that is. It probably is. Gonna call it a wolf because it looks like a wolf, or not because it looks like a wolf, but because there's snow on the ground. How many people have saw this post? So this was a researcher who made a debug build in C++ of Hello World. And then they compiled it in debug and uploaded it to VirusTotal. And it got this. Pretty much every machine learning AV flagged it as malicious. So machine learning isn't magic, right? It makes mistakes. And in fact, it was, in this case, the only thing that said that this Hello World script was bad. And there's actually a great post that came out explaining why. I think it was in Medium. I might have it in here. But so I'm going to skip that. And just get to the kind of the core assumption that we have here, is that if you're going to use machine learning, you have to have clean data. Because like we all know, garbage in, garbage out, right? You bring in garbage, you're going to get out garbage. And so let's kind of look at an example of computer vision again, and say, if you were trying to make a decision, make an engine that made a decision that said what a chihuahua looked like, there are probably certain things that you wouldn't be concerned about. I can tell you for sure for me that I wouldn't be concerned that this engine might consider a muffin a chihuahua. Is that going to the next slide? There, a muffin, a chihuahua. I mean, I guess they're pretty similar, but I wouldn't have guessed that up front. Similarly, I would not probably think that this would confuse a labradoodle and fried chicken, nor would I think that it would confuse mops with sheepdogs, although that one is really confusing for me. Sometimes I have a hard time differentiating. So I'm down to the 5-minute mark, so I'm going to talk to really briefly when it can not be used and when should it be used, and then throw you a bunch of pointers about more things that you can, more ways you can learn about this. So when is machine learning maybe not helpful? And I think I've tried to illustrate a couple of those. One is that your data is unique, very unique. And I guess in addition to this, I'm assuming that someone else is going to be providing you this machine learning model. So if your data is unique, and I mean legitimately unique, and someone else gives you a model, I think we kind of understand that with machine learning, data is a part of the program. You train this model using data. It's case-stratified cross-folds or cross-validation, right? So you perform this training, this cross-validation early on, but you're using data to do that. And if their data that they trained it on is not indicative of your data, then this may not help. because it's not going to generalize in that way. There's well poisoning concerns. So if some bad guy is slowly trickling bad things into your environment that's running it through this machine learning algorithm, and that this algorithm is online, meaning it updates itself, then it's going to start out as kind of normal because it's kind of innocuous and ramp up, and it's going to adjust. It's going to adjust to those changes and consider them normal, even as they slowly increment and become worse and worse and worse. So it's going to completely ignore that in certain scenarios. And this stuff is hard. So like I was just saying with the muffins and chihuahuas, that it's not super intuitive. So if you don't have really, really skilled people working on this, it's very easy to make really big mistakes. Hence, hello world, right? And I'm not even 100% sure that I would call that a mistake. But that is the sort of thing that could happen. There's also kind of live intuition and live interaction. So if you need to interact with something that's using machine learning on the back end, it needs to be intuitive. The best example for this I've heard is credit approvals. If I increase the salary that the person trying to get credit has, I need to be able to give them more credit. It needs to be intuitive. You're going to end up with something that looks like that alien, that alien connector for the bridges, where it's going to be very specific and it'll say, oh, even though you increased your salary, I still think that you should get less. I think in this case you should get less credit based off of what I knew. It could be very confusing. And then if your data formats are constantly changing, that might not be a good use case for machine learning because it needs to have things in a standardized format, and you can account for that, but it can get difficult. Deep learning is pretty much magic. I'm convinced a lot of it looks like this. There's even more examples than I gave earlier: boundary erosion, entanglement, hidden feedback loops, undeclared consumers, data dependencies, all kinds of different things that could affect your algorithms. So it gets complicated. But when is it useful? I think this is kind of the most poignant quote that I've been able to find on this topic is, if the environment is complex and feedback is delayed or ambiguous, algorithms will generally and relatively consistently outperform human judgment. So it could be useful when traditional methods are insufficient, when you can't do signatures, when you care about 0 days, when you have focused adversaries, and when you've hit the limits of basic anomaly detection and basic statistical information. When you need to speed up your first tier triage. And if I had to summarize this entire talk, I would say be careful if you're going to do machine learning on their own. And a primary use case in security for me is initial triage and suggestions on how to classify, not how to solve the problem. So now what? Machine learning is not magic. You need to find your company. If you're going to use this, find your company's balance between privacy, which is data collection, and data analytics. You need to have lots of data to do this, but you also need to respect people's privacy. So find where your balance is if you're going to do this. If you're interested in doing this in the next few years, I would suggest start now and pick a big data platform. Start shoving all the data into it and cleaning it up. Normalize it. Normalize it in whatever's okay for you, so that if you need to renormalize it later into a different format, you can programmatically and easily do that. But have it stored. And then for as long as possible, retain your data, because being able to go back and look at the history is a good indicator of the future. So I don't have any time for questions, because my timing is so impeccable that I got it right on the 0 here. But I did want to leave you guys with a couple of pointers to more, and I'd be happy to distribute these links, however, or the slides. But there is a Pittsburgh data science meetup group that meets, I think, the first or second Wednesday in the evenings or the late afternoons on the North Shore at the Microsoft offices. I would suggest if you're looking at a big data platform, and we can have a conversation about this if you're interested, but Apache Metron specifically for security data is a project that I'm a committer on, so bias there a little bit, but I think it's a good solution. The Hadoop ecosystem in general, and Apache Spark is also prevalent. And then I've also assembled some additional materials in InfoSec Labs, and there is a conference in DC on the 28th that I just found out about. I'll be there, which is going to talk about specifically applying machine learning on InfoSec use cases. And that additional materials is a gigantic list of white papers, and I'm sorry, I wish that I actually had the links up there so you could take good pictures of this, but I can distribute afterwards. Links of papers, white papers and presentations, and recordings of security talks at other conferences, and kind of a curated list of good information that I use to learn about this stuff. So that's all I've got. Thank you very much.